Welcome to the Chemistry Educational Series. Today we explore one of the most fundamental ideas in all of chemistry, the mole concept and Avogadro's number. Imagine trying to count every grain of sand on every beach on Earth. The mole is how chemists count the unimaginably small building blocks of matter. By the end of this journey, you will master how a single number connects the invisible world of atoms to the macroscopic world we can weigh, measure, and see. So, what exactly is a mole? In everyday life, we group things in dozens, in pairs, in scores. A mole is simply the chemist's way of grouping atoms and molecules. One mole contains exactly 6.02214076 times 10 to the 23rd elementary entities. Those entities can be atoms, molecules, ions, or any other specified particles. The symbol for mole is the lowercase m-o-l, written M-O-L. Think of the mole as a counting unit, like a dozen eggs, except each mole counts 602 sextillion particles at once. That is an unimaginably large number, but atoms are so small that we need an unimaginably large count just to weigh them on a laboratory balance. The number that defines a mole is called Avogadro's constant, written with the symbol N sub A. Its exact value, fixed by international agreement in 2019, is 6.02214076 times 10 to the 23rd reciprocal moles. The plane number, 6.022 times 10 to the 23rd, is called Avogadro's number, written N0. It is a dimensionless count. To put this number in perspective, 6.022 times 10 to the 23rd soft drink cans would cover the surface of the Earth to a depth of 200 miles. Avogadro's number is the bridge that lets us count the invisible world using the gram and the liter. The history of the mole stretches across 2 centuries. In 1805, John Dalton published the first table of atomic weights, taking hydrogen as one. In 1865, Joseph Loschmidt first estimated the number of molecules in a gas. The name mole came from the German word Molekül, coined by Wilhelm Ostwald in 1894. Jean Perrin named Avogadro's constant in 1909 and won the 1926 Nobel Prize for measuring it. In 1971, the mole became the 7th SI base unit, and on 20th of May 2019, the mole was redefined by fixing Avogadro's constant to its exact modern value. Count Amedeo Avogadro, the Italian physicist born in 1776 in Turin. In 1811, he proposed a hypothesis that was both simple and revolutionary. Equal volumes of different gases, at the same temperature and pressure, contain equal numbers of particles. Today, we call this Avogadro's law. The idea solved a long-standing puzzle about how gas volumes combine during chemical reactions, and it eventually led to the constant that now bears his name. Avogadro never knew the actual number. He died in 1856, decades before the first experimental estimates were obtained. Yet his hypothesis was the conceptual seed that made the mole possible. Without Avogadro's law, chemists would have no reliable way to relate gas volume to the count of molecules inside. On 20th of May 2019, the International System of Units was fundamentally redefined. The mole, along with the kilogram, the ampere, and the Kelvin, is now defined by fixing an exact numerical value of a defining constant, rather than by a physical object or a specific substance. Specifically, 1 mole now contains exactly 6.02214076 times 10 to the 23rd elementary entities. This number is the exact value of Avogadro's constant, fixed once and for all. The practical consequence is that any experiment anywhere in the world that counts particles can now be compared directly to a single, immutable number. The mole remains a counting unit, but its size is no longer tied to the mass of a carbon-12 atom, though for ordinary laboratory work, the two definitions agree to better than 1 part in a billion. The molar mass of a substance is the mass of 1 mole of that substance, expressed in grams per mole. Numerically, the molar mass in grams per mole equals the average atomic or molecular mass expressed in atomic mass units, or daltons. For example, 1 mole of carbon-12 atoms has a mass of exactly 12 grams. 1 mole of water molecules has a mass of about 18.5 grams, because 1 water molecule has an average mass of about 18.015 daltons. To calculate molar mass, you sum the atomic masses of all atoms appearing in the chemical formula. For sodium chloride, NaCl, the molar mass is 22.99. For sodium plus 35.45 for chlorine, giving 58.44 grams per mole. The molar mass is the conversion factor that links the mass of a sample in grams to the number of moles it contains. Avogadro's law states that the volume of a gas is directly proportional to the number of moles of gas, provided the temperature and pressure are held constant. Mathematically, V divided by N equals a constant. Doubling the amount of gas doubles the volume. Halving it halves the volume. This is the simplest of the gas laws, but its consequences run deep. It means that at any given temperature and pressure, 1 mole of any ideal gas occupies exactly the same volume. Helium, nitrogen, oxygen, carbon dioxide. A mole of any of them fills the same space. The identity of the gas does not matter. Only the count of particles does. Avogadro's law is the principle that turns volumes of gas, which we can easily measure, into counts of molecules, which we cannot. Standard temperature and pressure, abbreviated STP, defines a reference state for comparing gas volumes. The most common modern standard is 0 degrees Celsius and 1 bar of pressure. Under these conditions, the molar volume of an ideal gas is approximately 22.7 liters per mole. The older IUPAC standard of 0 degrees Celsius and 1 atmosphere gives 22.41 liters per mole. Either way, the principle is the same. 1 mole of any gas, hydrogen, oxygen, methane, or argon, occupies about 22.5 liters. This remarkable uniformity is the practical payoff of Avogadro's hypothesis. It lets chemists measure gas volumes with a simple graduated cylinder, then convert to moles by dividing by 22.4 or 22.7 depending on the chosen standard. Molar concentration, also called molarity, is one of the most common ways to express the strength of a solution. Molarity is defined as the number of moles of solute dissolved in 1 liter of solution. Its symbol is a capital M, and its units are moles per liter. A 1 molar solution of sodium chloride, written 1m, contains 1 mole, or 58.44 grams, of NaCl in every liter of total solution. To prepare 500 milliliters of a 0.1 molar solution of glucose, you would dissolve 0.05 moles, or about 9.01 grams, of glucose, then dilute to 500 milliliters. Molarity lets chemists work with convenient volumes while knowing exactly how many particles are reacting. It is the language of analytical chemistry, biochemistry, and medicine. The mole is the central hub of chemistry because it converts freely between 4 quantities: the count of particles, the amount in moles, the mass in grams, and the volume of a gas. This is the famous mole map. To move from grams to moles, divide by molar mass. To move from moles to grams, multiply by molar mass. To move from moles to particles, multiply by Avogadro's number. To move from particles to moles, divide by Avogadro's number. To move from moles of gas to volume at STP, multiply by 22.4 liters. And to move from volume of gas to moles, divide by 22.4. Every stoichiometry problem is a journey along this map. Memorize the 4 anchor values: molar mass, Avogadro's number, 22.4 liters per mole, and you can solve any conversion problem in general chemistry. Stoichiometry is the mathematics of chemical reactions, and the mole is its fundamental currency. A balanced chemical equation tells you the relative number of moles of every reactant and product. For example, 2 moles of hydrogen gas react with 1 mole of oxygen gas to give 2 moles of water. Once you know the moles of one substance in a reaction, you can find the moles of any other by using the coefficients of the balanced equation as conversion factors. The classic 5-step stoichiometry procedure is: 1. Write the balanced equation. 2. Convert the given quantity to moles. 3. Use the mole ratio from the coefficients. 4. Convert the answer to the units requested. And 5. Check that your answer makes physical sense. Master this procedure, and you can predict the yield of any reaction from first principles. The empirical formula of a compound is the simplest whole number ratio of atoms of each element in the compound. The molecular formula is the actual count of atoms per molecule. To find an empirical formula from mass data, 3 steps suffice. First, convert the mass of each element to moles by dividing by its atomic mass. Second, divide each mole value by the smallest of the mole values. Third, multiply by the smallest whole number that converts all ratios into integers. For example, a compound with 40.0 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen yields the mole ratio 1 to 2 to 1, giving the empirical formula CH2O. The molecular formula is a whole number multiple of the empirical formula. You need the molar mass to determine which multiple. The mole concept is not an abstract curiosity. It is the working tool of every chemist every day. In pharmaceutical research, moles determine the dose of an active ingredient in milligrams. In environmental science, moles per liter measure water and air pollution. In materials engineering, mole fractions define the composition of alloys and semiconductors. In cooking, even a pinch of salt is a measurable fraction of a mole. In batteries, the charge stored per mole of electrons is a fixed constant, 96,485 coulombs per mole, called the Faraday constant. In astronomy, the abundance of elements in stars is reported in mole fractions. From the food on your table to the stars in the sky, the mole is the universal translator that lets us count what we cannot see. Quiz 1. Question: how many particles are in exactly 1 mole of a substance? Option A, 6.022 times 10 to the 23rd. Option B, 12.00 times 10 to the 23rd. Option C, 1 times 10 to the 23rd. Option D, 6.022 times 10 to the 19th. Take 60 seconds to think about your answer. Pause here, and we will reveal the correct response shortly. Quiz 2. Question: what is the molar mass of water, H2O, in grams per mole? Option A, 10 grams per mole. Option B, 16 grams per mole. Option C, 18 grams per mole. Option D, 20 grams per mole. Take a moment to work this out from atomic masses. The answer will appear shortly. Quiz 3. Question: at standard temperature and pressure, what volume does 1 mole of an ideal gas occupy? Option A, 2.24 liters. Option B, 11.2 liters. Option C, 22.4 liters. Option D, 44.8 liters. Think carefully. The answer is about to appear. Quiz 4. Question. How many moles of carbon dioxide are produced when 1 mole of methane burns completely? The reaction is CH4 plus 2O2 yields CO2 plus 2H2O. Option A, 1 mole. Option B, 2 moles. Option C, 3 moles. Option D, 4 moles. Look at the coefficients of the balanced equation. The answer will appear in 60 seconds. Quiz 5. Question. Which scientist first proposed that equal volumes of gases at the same temperature and pressure contain equal numbers of particles? Option A, John Dalton. Option B, Amedeo Avogadro. Option C, Wilhelm Ostwald. Option D, Jean Perrin. Take a moment, then we will reveal the answer shortly. Problem 1. How many particles are in 3.5 moles of water? Let us walk through it step by step. Step 1. Write down the relationship between moles and particles. N equals N times N sub A. We are given N equals 3.5 moles. N sub A equals 6.022 times 10 to the 23rd particles per mole. Step 2. Substitute the values. N equals 3.5 times 6.022 times 10 to the 23rd. Step 3. Multiply. 3.5 times 6.022 equals 21.077. So N equals 21.077 times 10 to the 23rd. Step 4. Write the result in scientific notation. N equals 2.108 times 10 to the 24th particles. Final answer, 3.5 moles of water contains 2.108 times 10 to the 24 molecules. Problem 2. What is the mass of 0.5 moles of calcium carbonate, CaCO3? Step 1. Determine the molar mass. Calcium is 40.08. Carbon is 12.01. Oxygen is 16.00, and there are 3 of them. Step 2. Add them. 40.08 plus 12.01 plus 3 times 16.00 equals 40 plus 12 plus 48, which is 100.09 grams per mole. Step 3. Use the relationship M equals N times M. Mass equals 0.5 moles times 100.09 grams per mole. Step 4. Multiply. 0.5 times 100.09 equals 50.045. Final answer. zero point 0.5 moles of calcium carbonate has a mass of 50.045 grams. Problem 3. How many moles of gas occupy 11.2 liters at standard temperature and pressure? Step 1. Recall that 1 mole of an ideal gas at STP occupies 22.4 liters. Step 2. Write the conversion factor. 11.2 liters times 1 mole divided by 22.4 liters. Step 3. Cancel the units of liters. 11.2 divided by 22.4 equals 0.5. Step 4. State the answer. 0.5 moles. Final answer. 11.2 liters of an ideal gas at STP corresponds to 0.5 moles of gas. Problem 4. How many grams of hydrogen are needed to react completely with 16 grams of oxygen to form water? Step 1. Write the balanced equation. 2H2 plus O2 yields 2H2O. The mole ratio of hydrogen to oxygen is 2 to 1. Step 2. Find the moles of oxygen. Molar mass of O2 is 32.00 grams per mole. N of O2 equals 16 divided by 32.00, which is 0.5 moles. Step 3. Apply the mole ratio. Moles of H2 equals 2 times moles of O2, which is 2 times 0.5, or 1 mole of H2. Step 4. Convert to grams. Molar mass of H2 is 2.02 grams per mole. Mass equals 1 mole times 2.02 grams per mole, which equals 2.02 grams. Final answer. 2.02 grams of hydrogen gas react with 16 grams of oxygen to form water. Problem 5. A compound contains 40.0% carbon, 6.7% hydrogen, and 53.3% oxygen by mass. Find the empirical formula. Step 1. Assume a 100-gram sample. That gives us 40.0 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. Step 2. Convert each mass to moles. Carbon, 40.0 divided by 12.01 equals 3.33 moles. Hydrogen, 6.7 divided by 1.008 equals 6.61 moles. Oxygen, 53.3 divided by 16.00 equals 3.33 moles. Step 3. Divide by the smallest. All divided by 3.33 gives the ratio 1 to 1.98 to 1. Rounded to whole numbers, this is 1 to 2 to 1. Step 4. Write the empirical formula. C1H2O1 or simply CH2O. Final answer. The empirical formula is CH2O, which is formaldehyde or any sugar building block. Let us summarize the key concepts. The mole is the SI base unit for amount of substance. 1 mole equals exactly 6.02214076 times 10 to the 23rd elementary entities. Avogadro's constant, N sub A, is 6.02214076 times 10 to the 23rd reciprocal mole. Molar mass M is the mass of 1 mole of a substance in grams per mole, numerically equal to the atomic or molecular mass in daltons. Molar volume at STP is 22.4 liters per mole for any ideal gas. Avogadro's law states V divided by N is constant at fixed temperature and pressure. Molarity is moles of solute per liter of solution. The mole map links grams, moles, particles, and gas volume. One last formula to remember. N equals M divided by M. Mass divided by molar mass equals moles. Memorize this, and you hold the key to stoichiometry. And so we come to the close of our journey through the mole concept and Avogadro's number. We have seen that a single number, 6.022 times 10 to the 23rd, bridges the visible and the invisible. We have traced the history from Dalton to Avogadro to Ostwald to Perrin. We have explored molar mass, molar volume, molarity, and the mole map. We have applied stoichiometry to real reactions and derived empirical formulas from mass data. The mole is more than a number. It is the language in which chemistry speaks. Every equation you balance, every product you synthesize, every analytical measurement you trust, all of it rests on the mole. Carry this language with you into the laboratory and into life. Thank you for joining us in the Chemistry Educational Series.